Should, well, so we are recording now. Hello, everyone. This is part 2 of the workshop. Me and Max are both very excited to have you here. And the bulk of this particular session will be focused on the Python aspect. So I'm going to go through a lot of Python, but first, do all of you have like a working Python environment, or where are you coming? We got one thumbs up. If you don't, that's okay. Maybe you're just here to watch. Anyone else? Okay. It's early in the morning. So the way that I was thinking of, and keeping in mind that this will be recorded and there might be people who have never used Python before, I was going to start my workshop showing how I open up my my Python environment and then go through the 2 sample scripts. And then from there, I can do some examples of how to like build upon some of the scripts and general troubleshooting questions if people have specific things that they want to do in Python. So I'm going to share my whole screen. And so I'm on a Windows computer. So the first thing I do, I go to Anaconda Navigator. And also keep in mind that you can do all this stuff with pip, but I'm not really a good resource for showing you how to do pip. The way I open my Anaconda Navigator is through the GUI, so through like clicking and stuff. There is technically a way to do it all through the terminal, but for some reason on this particular computer that has never worked for me. So this is how I do it, but it's fine. And it is a little slow, so bear with me. So the first thing I do, I have my different environments. Instead of in the terminal writing conda activate earth analytics Python or whatever your environment is called, I literally have to click it here. For some reason, when I go to open like Jupyter Notebook or Jupyter Lab, it just won't do it from my terminal. And I've never bothered to fix it because this works fine. But it does take longer. And it might be taking longer because I'm also on Zoom. My 8-year-old laptop. All right, let's go. Not responding. Give it a moment. All right, our environment is now active. So then I go to the Home tab. And for you, if you've just downloaded all of this, you might need to install the things you want to do, but it makes it really easy here. You can click install or whatever. You can use, the scripts I wrote some of them in Jupyter Notebook and then open them in Jupyter Lab. I prefer Jupyter Lab just because the GUI is a little bit nicer if you're looking at a lot of different scripts and you're making a lot of plots. All right, things are really going slow. All right. So what we're going to look at today are these two scripts, which are both in the Google Drive. And if we add more to it and there's more functionalities, I'll add a second edited one to the drive. So this first one is the downloader, in which we query the satellite data from Google Earth Engine API. It downloads, and then we can either just like have it in our workspace or we can save it. In the Google Drive, I've also put something called a .mpz file. So if like this is not working for you, but you still want to follow along, you can see on Big Moose Viz, or for visualization, this is more of like, this will allow you to just load in that NPZ file. But what I'm going to do is show you how to create that NPZ file. So you have the data, and then, you can change it for your shape file, for a time period, for any other certifications. So I've already run this, but maybe it's helpful, especially for new Python people, to show how to run it. So generally you can restart and run all. With the Earth Engine authenticate thing, it only needs to be done once a week. So, but if you comment this out when you run it, it'll like prompt up like some type of internet tab. If like for right now, I'm doing Jupyter Lab on Microsoft Edge, but I take that link and I put it into Chrome because that's where my Google Chrome account, that's where like my Google account is logged in, and then just like click a bunch of things until you get a code and put it back in here. But then here, if it's already logged in, then all I need to do is initialize. So I'm going to restart and run all my cells because it'll probably take a while and I can talk about it. So these are just the packages that will help you do basically a lot of plotting and a lot of manipulation of the data. You can add toolbox as you need or as you want. Pretty easy to add to your Conda environment. I'm going to check the chat right here. Okay. Thank you for dropping the link. Okay, so if this comes up, this means I do need to authenticate. So here I've got, I say generate token. Wow, everything is going so slow to me. I click on my account. I say continue. It hasn't verified the app, but that's okay. Select all, continue. And then I copy the token. I put in here. And then it's great. It's like, now you're connected. And then I comment out EE authenticate because I won't need to do that for another week. These are the little functions that just make different things below a little easier. Just comment them in. And then this one here is where we turn your existing shapefile that you have stored locally on your computer into a Google Earth Engine object. And so you'll notice we brought in Google Earth Engine as EE, and then we also imported GEE map, which is that extra little toolbox that does a lot of things. In this case, the only thing I use it is to turn your shapefile into an Earth Engine object. So this is Google Earth Engine's version of a shapefile. So here, like, especially if you have like, for me, I wasn't just doing one lake. I had an Excel file with all the lake names, and then I had my shape files. named all the lake, but with no spaces, because a lot of the time Python and most coding language don't like any spaces in like file names and stuff. So I used one of those functions, remove, to remove all the spaces out of that. And then I tell it to look in my folder with the shape files. But for you, the path will be kind of like wherever you've put it in. And one note is that if you have a Windows computer, you have to manually change the direction of the slashes from a backslash to a forward slash. So like Windows will always give you the path with a backslash, but most coding languages require paths to have a forward slash, so you have to change that. Which is an annoying thing that no one has, figured out yet. Okay, so now I have my EE object. So it's whatever the shape file I've specified, Big Moose Lake. Here is a really massive length of code. And I'm gonna turn on the line numbers for this. So I'm going to go through it. I'm actually going to start this running, and then I'm going to go through it while it runs, because it seems like everything is taking a long time. So I hit enter, and this will have that little star for a while because it'll be working. And it'll also print out this lake will have 32 images, and then it will also print out after it's done every image, kind of for those who want their own little counter. You can also comment out that print thing, but I prefer to have constant reassurance that my code is working. Okay, so let's start with lines 4 through 12. This is very similar to the Google Earth Engine script that Max showed, in the sense that we're calling the collection. So instead of loading it in as a variable, we call it in here saying EE image collection. This is where we're specifying the satellite and then the properties. So this is like collection 2, tier 1, level 2. And you can find all of these codes in the Google Earth Engine catalog, which is connected to the code editor and stuff. And if you're doing it, you'll be looking at the catalog, and where Max kind of show you to look at all the bands. That's where you find this information. So let's see. Are my images loading? Okay, it says image 0 is okay. Python always starts counting from 0. So that's something to be to have in your brain. Then I specify my dates. So for this, I just wanted all the images for 2022, basically. But let's say you want all the years, but specific months. I've just commented out a line here that you could do instead. Like, for example, if you want June, July, August, you have calendar range, like the 6th month to the 8th month, and that works. These numbers don't need to be backwards. Like if this was all in Pythonic language, potentially, then you'd have to do something like 5 to 7 for months 6 to 8. So it gets a little tricky there, but don't worry about it. Like I said here, if you plan to do additional cloud filtering later, keep the cloud filter at 50%. If you don't want to do additional cloud filtering later, which I would recommend you do, you could play around with this number and, see how many images you get if you turn it down to like, you only want images with less than 10% cloud filter. And then I'm just saying sort by date acquired. This is that first print thing. So after it's done that, it tells me how many images there are in this here. So you have an idea of maybe how long your process is going to take. This is just a little like, whoops, you had too restrictive filters and you didn't actually find any images at all. Then there's a bunch of stuff here that you don't have to worry about any of this, but you do have to worry about 31. So 31 is where you list the bands that you want. So maybe this is maybe a little different than like you have to specify which bands you want. So for me, maybe I only want surface temperature. I could delete all of this out of the way, but I've set it up in basically having all the main bands surface temperature and also the QA pixel, which is really important for like land cover and clouds and all of that stuff. But keep in mind, if you change the bands, it also means you have to do a lot of copy and pasting below. It's not the, yeah. So but it will take less time. So then here on line 39 starts our triple nested for loop. And the reason it is triple nested, and that means there's 3 for loops, which maybe some of you coders are like, that's really inefficient. But this was the way that I decided to construct my 3D arrays. So the way that this works is that it will create an array, and like that is generally like for each band that you specify, it will create an array that has the dimensions of lat, lon, and time. So you have a 3D array for each of your bands. And that is why you have so many different things here. So the TTAR, that's like time array. And you have time, you have red, you have green, you have blue, you have aerosols, you have near infrared, you have shortwave infrared, you have shortwave infrared 2, and the QA pixel here. Also, this code should work for other satellites as long as they have equal area projections. So because it's a 3D matrix and the way I've set it up, there's just one lat lon vector for each. It doesn't, like if you have the other types of projections where it's not approximated to a perfect square, then you're going to need to do different things, and that would be like outside the scope of this. But I just want to put that warning here. This is where we do all the lat lon stuff, assuming that it is equal area projection. Then we say initialize all these and then try to get that data. The data comes in a really long vector format. And then we're going to scale and offset it, which someone asked about in the last workshop. This is where we just apply those scaling factors that you can also find in the catalog. And then we initialize the 2D arrays to go into the 3D array. So the reason I do this is to make sure that there's always a clean array for the process to basically put all the vectors into a nice 2D array that's already clean. There's no like mess up of numbers, and then we add them to the 3D array. And this is because sometimes random pixels will be like weird or not work, and that's fine. We just don't want like any of that data to carry over. This is then the lat and the lon. So y is the latitude, x is the longitude axis, and this is a double for loop here, where basically you go along the y-axis, and then for every x coordinate underneath, so you're going basically in a grid, you take that long list where you're finding like that one, and then you insert it into your 2D array. If there's an index error, we pass it, and then if all goes okay, all of that worked, we put that 2D array into the 3D array. If for some reason that scene was really bad, something happened, there's a lot of like issues, then you just fill it with an array of nans. And then it'll also say that that image was bad, so you know to delete it later. As you can see, this is going painfully slow, which is to be expected. The lake has 32 images and we're only on image 10. But we'll wait around. So then I'll go over the next point, which is so I'm just checking. No, any more questions in the chat? This is how to save an NPZ file. So if you want to just save all your data in that 3D matrix, you can totally do that. And it's NP saves. And then you just have to specify the variables that are NP, like NumPy arrays that you want to save in there. And then this also shows you how to load all of that in. Let's say if you have your NPZ file loaded in. And then here are a little bit of checks that we can do afterwards. But what we can do is transition to the other and let this run, and then I can show you later. But perhaps this is a good time. I know this is like a massive piece of code, but hopefully when you go to manipulate it for your own needs, it's not that complicated. Does anyone have any questions at this time? No? Okay. So let's go over. Yes.
Hello, Carolien.
Yes.
Sorry for interrupting you.
That's okay.
I see line 191, T-tar.
Yes.
Yeah, a little bit. Would you explain that one? For example, the bracket, the colon.
Yes.
What?
Yes.
Explain a little bit.
Absolutely. So these brackets represent basically the position in which you want to put the 2D array T-tar into the 3D array T-tar, or T-tar, and this is TR. So this is like time array, and this is this is temperature array, and this is temperature time array. So you can think of the colons, and the colons mean everything. And then T is specifying the time that we're on, which corresponds to this T, which means for each satellite image. So you can kind of see up here when we first initialize it, each of these time arrays, so the 3D arrays, have the length of the latitude columns, the longitude columns, and then how many images there are. And then we take our 1D vector, which comes from here. We initialize those 2D vectors. Here we're putting those that 1D vector into a 2D vector. And if everything is okay, then we put that in here. And this is the difference here is, we're basically this part here is the same as this part, but we have this whole except thing here just in case something goes wrong and this image is really bad and we don't have data. It just creates kind of like a dummy one just so the loop doesn't stop, full of nans, and then we insert that into there. Did that answer your question about the
Yes. Thank you for that
okay.
one. Okay, my last question. You put T on the bracket at the last place, yes? Still
Yes.
on line 191. What about if we put it in the first place, inside the bracket?
So that would basically that would like mess everything up essentially, because what we have is like TR has a size of like latitude via longitude. So I don't know, maybe there's a way for me to draw on the screen. Hold on. Gonna annotate. So you can kind of think of your 3D array is like, it's a grid, but then it's also 3D. All of these cells have a value of like, let's say temperature, right? So that's your band that you've taken, or it's like the blue band or the red band or whatever. And let's say this side is lat and this side is lon, and then this is time, but really it's like image 1, image 2, image 3. Okay, and this is 4 by 4. So actually I'm just gonna make this one 5. So the lon is 5 long, the lat is 4 long, and time is 3 long, just so we can show. So this T tar here, the array is basically like, okay, let's see if it's lat or long first. I'm not going to be able to see, but let's assume it's lat. So it's going to be the length of lat. So like 4, 5, 3. So basically T tar is like this box, and then T, and so let's say we had T, which like, let's say it's like 2 right now. What that basically says is that, like, let's say it's 2, or in Python that would be 1, so it's like the second but it's the 1. That would mean you're taking a 2D array and you're kind of putting it like where this one is. You see, so you're kind of like, if you want to think about it spatially, you're kind of like inserting chunks of data into this 3D matrix. So that's the second one. And let's say if you put okay, draw that back. If you put, let's say your question was if you put instead 2, comma, colon, comma, colon, let's just say T was 2, and this was lat lon T, would that would be instead this chunk here. And I realize my lines are not perfect. But it wouldn't work because the like T would only be 1. So actually it would like try to just fill like this area instead. And then the code would freak out because it's like trying to fill up like a weird amount of space that there isn't the right amount of space. Like it'd probably like be sticking out one way, like spatially it just like wouldn't work, and then the code would like stop running and say like we have a problem. Does that make sense? Okay,
Thank you,
great.
Carolien.
Okay, so let me exit. Can I scroll again? Okay, I'm going to delete this, but also I just want to show out that you can keep track of which one is lat, long, and T here, because you see n rows, n calls, count n. So you go up to, okay, n columns, the number of columns is equal to the unique number of longitudes, and n rows is equal to the unique amount of latitudes. So perhaps if I was a better coder, I should have done like n lat and lon, but you know, I didn't. But remember, like if you're confused, you can like always go backwards in like what all the variables mean, and usually you can figure out stuff that way. Okay, let's see. Did this finally finish? No, not yet. Okay. I'm also going to clear this annotation. Clear all drawings. Cool. All right. So while this is doing it, let's go to Big Moose Viz, which is the visualization. So you'll see this has maybe a few extra things, but we actually don't need any of these shapely ones right now. And also, if you want to comment out stuff, you can do control / and I am going to upload new versions, so you don't have to like worry about if you have Shapely. Although if you did follow my instructions, you will have Shapely already. Shapely is good if you're trying to mess around with spatial shapes and such. So let's load that one in. And I think things are going to be going really slow because this is working so hard. And okay, we have our little functions. And then this one will run basically on your NPZ file that you should have downloaded. And here we're going to go through cloud filtering. So I agree with Max when he said, like, these are complicated. They are complicated. There was a great Medium article that I took most of this data from, and I don't know if I credited it here, but if anyone's really interested in understanding Bitwise and understanding more about how this worked, I can dig up that article online, and I thought it was a really nice tutorial for this kind of stuff. So basically, I'm going to run this. We're going to see some stuff coming up, but let me explain it. Basically, all you need to know is that this is your dictionary. Okay, we have. Yes, okay. I will make sure to send the article by the end of this workshop when we have this stuff. So this is basically your dictionary, just saying what the different QA flags mean for different QA pixels. And keep in mind that these numbers change for every satellite, even Landsat 1. So Landsat 7 has different flags than Landsat 8. It has different flags than Landsat 5. There are these really horrible, like 200-page Landsat documents where you can technically dig this up, but it's really nice if you find something that, you know, distills that information the way you want it here. But yeah, Bitwise can get a little hairy and confusing, but hopefully this will set you on a nice path to do it. So here we load in our array, Big Moose Watershed. We load it. We allow the pickle. I don't know why. It only works if we allow the pickle to be true, I guess. And then we basically take, if you want to see everything that's in, maybe you've forgotten what's in your NPZ file, you can do, I call it beep.files. It will list like all of these names for you. And then I've just re-put them into little, into variables just so it's easier to work with down below. This is some stuff. So this is more Bitwise stuff. This will help create this is like your function. So if I wanted to, I could, well, it would have to be, you need this function is not up here because you need the L8 flag dictionary here for this function to know what it's doing. And then I say cloud masking is going to start. So here I'm getting that, so the same way that we kind of had a specific lat, lon, and time length for each 3D matrix, I'm just making sure we have that to start with, because every lake or every space that you're going to have, like it's, and even if you have the same lake, but it's a different band, it might have, like, ideally it's all the same, but you know, like you want to make sure you're always grabbing that information kind of in the moment. We don't have to talk about this, but this will count the number of non-nan pixels in the lake. And then we're going to create a fresh new empty matrix for our mask once it's been cloud masked, so we can like dump it in. You can see the same length variable, so x, x, y, y, z, z. And then I fill that all up with nans. All right, now, okay, it's just one for loop, so it's not a stress. No, it's two actually. So for each time in each lake's array, do a mask. So that means we go in, we say, we query ftar is just like the one for the time. For the QA pixels, we have to convert that to integers. This is just like annoying little things that I had to do. And then here is where you define what you want to mask. right? So I'm saying that clouds, you have to for Landsat 8, you have to specify the clouds. So it's cirrus, cloud, dilated cloud. Shadows, it's a little bit easier. It's shadow, and here I'm concatenating. So, or sorry, I'm not concatenating here, but I'm just making a third one, which is like, I know I want to take out the shadows and the clouds, but I'm going to show you how it looks for all three. So I'm going to combine cirrus, cloud, dilated cloud, shadow. Then you do a bunch of these things here. And this is really where the masking gets done. So you're just saying, like, based on like, because these will return these nice little matrices that are just 0 and 1 for like the mask. Because a mask essentially like gives you a matrix of 0 and 1s, the exact size of the thing you're trying to mask. You multiply every value by 0 or 1. The ones by 1 remain. The ones that are multiplied by 0 are now 0, and then you have your masked array. So here we're finding where they are, and then we mask them here. And for the recording, I am told that will be available next week. Then here, for RGB, this is just so we can have a true color image if we want it, which is kind of unnecessary, but I set you up with some nice visualization tools. We're going to set some up. This is just more like, I should really say that, yeah, I mean, here it says that it's RGB, but this stuff all the way down, this is just to make an RGB image. So like kind of true color, but you'll see it doesn't really look like true color. It doesn't really look like the world. Then we have our masked one. Yeah, that's the RGB. And then finally, we're all done with that. Now I'm like, show me everything. I want to see the clouds. I want to see the pixels that are clouds. I want to see the pixels that are shadows. I want to see what the original image looks like. I want to see what the cloud mask data look like. And I want to see the RGB image. And clearly, the RGB image looks very strange for the first couple images. But then here, you can kind of see it's like greenish blue, so it kind of works. I was never fully satisfied with the RGB images from Landsat in this sense. But this gives you a good idea of like what the cloud, what your pixels over the Lake of Big Moose look like when you have clouds, shadows. And this one is weird, right? Because it's just on the edge of the lake. So you might think like, was the QA pixel wrong there? Did something happen? But there's also a lot of shadows. So maybe it's confusing a shadow with the cloud, but we just get rid of all these suspicious pixels anyway. So like this one, very cloudy. And you can see like and some days you end up with a super small amount of data, right? So like here, but then some days you end up with basically the whole time here. But it comes a time where you might want to remove these data points. And that's why I say calculate the number of pixels in the lake, so the number of total pixels in the lake, so that later, if you're like doing some data cleaning, you can say, okay, like if they're less than like 10% of the original pixels in the lake, I'm just going to get rid of that entire image because, like the whole thing was basically cloudy or shadowed. Like, I don't know how much I really want to rely on, let's say, like that little blob right there. Right. Okay, any questions about the cloud masking so far? Okay, I'm gonna take that as a no. Let's go check on our other script. Okay, I think we're done. Are we done? Yes, we're done. Oh. Okay. So I'm gonna avoid saving it for right now because I already have a save, but you'll just have to change this for your own personal directory. You could also like not put any of this and just like specify the name of the NPZ file you want, and that will save in whatever local file, whatever local folder you're working in currently. All right, so let's look. I want to see. Oh. Okay, this is actually only going to work if I save it and then load it in. Sure. Interesting. I called this Big Moose watershed. Sorry, guys. I hope that's not too confusing. And I have all of my things in here. And I would say this is a very nice way to have a good look at just one image. And so I've done surface temperature here. And I can change this for any temperature scene. So first, let me see. There were 32 images there, but let me, like, perhaps I just want to know what the size is, right? So I could do the size, or that will give me the entire vector. np.shape, I can see the lats were 121 long, 266 wide, and 32 different satellite images. So let's say instead of the 15th one, I want to look at the third one. I can change that number there. And here we can see it was quite cold, and that's because it was February here. But this is a nice way to visualize one part of the lake. Obviously, you will, if you're looking at something like a different band, you will have to change this color bar. But if you are into temperature, basically this whole thing is devoted to making this beautiful, nice dual degree color bar, which I'm very proud of. But let's say like you're trying to make a map, putting just like the number of pixels, that does not work, right? People are like, what do you mean by 120, 250? This doesn't help me. So generally we want lat longs on those axes instead. So there's a bunch of steps here. We do longs, lats. We have to do a little bit of flipping and stuff just because in the North America, you have negative longitudes. So these values are negative, so you have to flip things just to make it plot nicely. But now we can see what the lat and longs are. So that's just like a little extra functionality. All right. And this data down, this stuff down here is just basically substituted for another shape file, which could be for the watershed. So I feel like we should take a little break right now, perhaps give people a chance to stretch their legs and think about if there are other specific things they want to ask about for the rest of the workshop. Does that sound good? And I can also find that article while we take a little break. Okay, great. So I'm going to stop my sharing for now. It's 10:49 now, so how about we come back at 10:55? Hello, everyone. How are we doing? Exhausted from just looking at that code? Hopefully not. Okay, so for this next portion, we I think there's a lot of flexibility here. I was going to show you all how to condense a 3D matrix into a nice time series, but if anyone has any suggestions or like things that they want to learn how to do in Python, within reason, you could like put something in the chat or ask a question or like turn on your mic. I really want to hear what would be useful for all of you. No questions? Okay. I will do a time series then. All right. So I'm going to go to Big Moose Viz. And again, when I update this, I will upload the new version to the here. I will upload the new version to the Google Drive so you can all have this, right? So now we've done all this cloud masking, and right now I don't want to look at any of these pictures, so I've minimized them. But now we want to do stuff with our cloud masked data, right? So that is going to be TZ, right? So everything we're going to want to do is like TZ. And then I'll also show you how to export that thing from a CSV file. Once you build up a good amount of code, most of what I do is just look at my old code to see what I've done previously. So let's check out annual viz. And I'm going to put that over here. My computer's struggling. So let's look. Okay. Where's I don't want this one. Let's see. I just want a good old time series. First of all, let's look at TZ, right? So let's check it out again. I think it's good to understand what your data set looks like. So if we want a time series of that would give us 1 point per time, that means eventually we will want something that has essentially a shape of just 32. So I mean, implicitly it'd be like 1 comma 1 comma 32. But basically we want to average over a certain axis. And the way that we're going to do that is here. So this is NumPy nan mean, and then we say LST, but in this case, we're going to change it t underscore z, and then the axis 0, 1 essentially means this axis here. And I'm sorry, I can't explain it more to you, but let's check it out and see if it works. You don't have to worry about that mean of empty slice because we've left a lot of empty spaces in the place where the lakes aren't are, so you're always going to get these things. So now let's look at what does LAR look like. So LAR is now it's 32, which means we have done it. And you also might have noticed that LAR, there's one nan, right? So it was probably when we looked at all of our images and one of them was like completely empty. Yeah, this one. So this one is going to show up as a nan. So really we should remove that and stuff, but let's just run it and we'll see what it looks like. All right, let's do some plotting. Where's my time axis? Do I have a time axis somewhere here? Yes, so I have time. Also, I will say something that I spend the most time with in Python is dealing with different datetime formats. So I'll just leave you with that. Like sometimes it's really easy, sometimes it's difficult. I just like basically Google how to do if it's not showing up. If they're not showing up, then you just Google how to do it. Okay, so now we know we have our time. We have our spatially average thing. And now very simply, we do PLT plot, and let's do time, comma, R, and see what happens. Right? Okay, here we go. And it's nice because if things are in datetime, when you use plt.plot or the PLT library, it can interpret those as dates, and you can also switch those dates. But this is not very pretty, right? So let's make this prettier. Let me.
Carolyn, you have a question in the chat. Suzanne asks, what are the elements of datetime, year, month, day, and then ...
Year, month, day, hours, minutes, seconds. Now I'm gonna steal from something else. Let me see. Where do I have some nice plotting things? Like for me, I'm like, if I know I've done this once, why would I ever do it again? Because I can steal some of my nice plotting things. Okay, where is... So for example, I want some titles, I want some labels, I want them to be bold. Generally, you want to put these things after you've already plotted it. Title. Spatial average of big moose land. For sure. And then Y label. Who's keeping track? Are we in degrees C or are we in degrees F? Did anyone check? That's something you also want to look at. There should be pretty good documentation for this back in our matrix maker. Oh. So STB10, let's look. We get the info, scale and offset. I have, this is when I've converted it from Kelvin to Celsius. And do I convert it anywhere else? I don't think so. So let's look. And then what do I do here? I plot it as degrees F. So we're just going to assume that I plotted that in degrees F. And let's also see if that makes sense for our numbers. Yes, this looks like degrees F to me. So LST, and I also want this to be nice and bolded. Right. Okay, great. Maybe I want a scatter plot instead. Let's see what that looks like. Right? We can do all types of things. And probably what a lot of people want to do is to do a linear fit. Right? But keep in mind that anytime you're doing like a linear fit, you also want to check the significance, and there's a lot of other Python packages in which you can do and check the significance. So let's say, okay, my vec here in this code that I've set up is my x value, so that's going to be lar trend. My x num, oh wait, yeah, sorry, my vec is my y, and then my x num is time. Let's see if that works. Okay, there's another date time thing. I have to switch. I'm sure I'm happy. So as you can imagine, date time does not always, you have to do something to it first. Here we go. Xnum equals dates, date to num. So you're switching the date time into a number. And I don't want to go too much into that, but there's a lot of coding for, so a lot of coding languages have their own like base way of understanding time, and there's all these different weird names for it, and some of them are really weird, but it's something you definitely sometimes just need to Google. Like for example, I came across one recently that I'd never seen before that was like, it just counted time in terms of minutes from 1850, like January 1st, 1850. There are other ones that are like seconds since January 1st, 1970, which is kind of like when coding began. So people like these coding languages, and then they have these numbers. So let's see if this works, and I'll show you what the date times are. Okay, so here we go. Here's our trend, right? But like keep in mind, this is such a weird data set, right? Like you see it literally, well, it's not weird, it's just like it goes from winter to summer to winter again, which means a linear curve is not really what you want to do, right? Like that would be a poor statistical operation to perform on it. So you don't want to do it. But I just want to, but perhaps if you had just summers over the past couple of years and you want to see if like the temperature in June has been rising, that might be something a linear fit is good for. Also, I just want to show you, let's see what xnum is. Yeah, so you can see it's like these numbers are like 1900 whatever, and who knows if these are days, seconds, minutes. These feel minutey to me. But anyway, there are these random numbers, but then there's always going to be functions that, like, for example, basically I turn it into xnum so I can do my polyfit, which gives me, but I'm doing a linear fit. And then when I turn it back, actually it just knew already. So the nice thing, sometimes I've converted things back, but here I didn't need to because PLT Matplotlib already knew how to convert datetime, and Matplotlib knows the average person doesn't want to see these numbers. They want to see what these numbers look like in daytime. All right. Has this prompted any questions? Or like, do people want to see other stuff? No? Okay. Then I will just show you how to save to a CSV file. So again, I'm looking at a time when I know I've done this before, because maybe I figured out a really nice way to do something and I don't want to forget about it. So this touches on a few things. One, we are turning our data into a pandas data frame first. So here we can specify, so in this case, we specified the variables and the name of the variable. So I'm gonna say time, and put our degrees. So I'm gonna put LST, and we have, what are we calling this? lar, and let's call this great. Okay, now I have a CSV. Let's go look if this will ever load. It's tragic how slow this is. In the meantime, I can also show you what this data frame looks like. So pandas, no? And I spelled max wrong, so it's amax. Cool. So this is my data frame, right? Pandas data frame, very easy to construct, but you can see it's very similar to a CSV file. And you can also see that Pythonic stuff starting at 0 and then counting down. Once something is in a pandas data frame, let's see. So it gets saved locally on your computer. And if I've just done this, this is going to save to whatever folder I'm in right now in that code. So I'm showing you. So here you can see Adirondack Lake code is where all of these things are open. And so this gets saved. If you want to save it to a specific location, this is where you could put like path, like folder 2, like whatever. You could do that and have it saved to a very specific area. But that's not going to work. But then also the nice thing about Jupyter Lab is that you can, if you're like me and you want to triple check everything, you can also just like click on it and be like, okay, my CSV file looks relatively the same, and you can also open it in Excel. And I still have this empty one. So another thing we can do is a little data cleaning. Any other questions? Okay, let's try to get Pandas to drop this nan here. So hmax or hh max. If you want to query a specific thing in Pandas, what you're going to do is, and I can do tab complete, or should be able to do tab complete. And here spaces don't matter in your names, but generally I avoid spaces. So for example, I'm just showing you this kind of indexing thing. So if I want to do this, I have to make sure everything's spelled right. Oh, okay. Equals equals. I want it shown. So this is how you get one thing, right? Maybe I just want to see, where is this less than one or less than? See, and it comes up with a Boolean thing. So then I say, but I actually want to see what those values are. So you can do little functions within that to say, okay, I want you to filter this, and here's this. Oh, there is I think that's the function. Here, okay, so here we have, now we figured out which one is the nan. So it's not equals equals nan, it's is nan. Also Python likes these double equal signs for when you're trying to like evaluate something. So I'm gonna do PD, I think it's drop, this one. Let's see what happens. Okay, I can't remember it off of my head. So then I go look through my old code. See my color things. So a lot of Python, I would say, is just Googling how to do things. Let's see. But I won't drag you all through the process of me Googling how to do things and all of that, because I think you can all do these things yourself. But there's a lot of data cleaning methods. There's a lot of other things you can do. As you can see, it's sometimes easy, sometimes pretty, and sometimes, you just have to you have to build up your own code and hack around until you get something right. Yeah, are there any questions? Drop NA is also a function. Thank you, Jorit. Let's see if that works. Yeah, perfect. Thank you for that. So hmax dot drop NA will drop essentially any row that has an NA in it. So then you have your nice clean data set. And perhaps, yeah. And then also, so if I want to save that, I'm just gonna call it like TT. And then because it's a pandas data frame, you can also, there's a lot of like little functions. Just okay, you would have to set time as your index, and then you could do that. But there's little things in there. All right. How do we all feel? Great. Okay. So there doesn't seem to be a lot of like burning questions from the audience right now, but does anyone have any questions for Max with the Growth Engine code editor? I don't want to put you on the spot, Max, but I feel like it might be a good time to check in on that. Could you elaborate a bit on using shapefiles for cutting a TIFF? That is something I've never had to do, but or raster in general, that bitwise masking code is probably a good place to start if you aren't able to find some code online. So in general, a TIFF or raster, like as you know, is going to be like a bunch of things. And if you want a shapefile, you're going to want to either get like the outside or the inside. And I'm trying to think, like, I think Shapely, that toolbox Shapely might be of help. But because I haven't done that or done that very recently off the top of my head, I wouldn't be able to like tell you right now. All right, any other questions? All right, well, I just want to say thank you so much for all coming and listening. I hope this was informative. I hope you learned something. I hope this will make some of your Python experience better, easier, maybe more efficient.
Yeah, thanks everyone for attending. If you have any questions after this that come up when you're running through with your own data or anything, definitely feel free to email either or both of us, and we'd be really happy to meet with you and help you out.